So a new Apple exploit has just been published, which attacks physical characteristics of the M1 silicon chip itself. So it's claiming to be unpatchable. So I thought it would be fun to kind of go through the details, kind of get an idea of how it works and what the actual impact of that is. The researchers who have developed it have called it GoFetch, and it's not really an exploit these days unless you have a website, a name, and a cute logo. So they've ticked all the boxes here. So let's dig into it. I've kind of had a bit of a skim through it, and if you want just like a high-level overview of what's going on, then any of the blog posts or tech articles that have covered it will give you like, you know, a really good high-level summary. So if that's kind of what you want, then that's absolutely fine. You can go there. However, if you want to dig a little bit deeper, like I do, then we're going to do that now. My first instinct with anything like this is just to run it. Like, I want to see the code, I want to see it running, I want to see what it does. So if we go to the GitHub link for tools, we can see that it's just a README, so this really doesn't provide us any great insight into what's going on. However, they do have a white paper, and that's what we're going to read through now. We're going to go through the research paper, kind of pull out the salient points and get a feel of what's going on. So this is a classic 2-column LaTeX research document, which gives me massive flashbacks to my days at university. Starts off in a pretty standard form. We've got the abstract, the introduction, what, you know, their contribution. It's all kind of just standard research paper chuff. Read it if you're interested. But the first really important information for me is the background. So this really just covers some important background information that you kind of need to know in order to understand this exploit. So the first thing is cache architecture. So modern processors use a hierarchy of caches to reduce memory access latency. What this means is that when you have some code and it accesses some data, say an array, and it indexes into it, the CPU will have to go and fetch this data from RAM. So that's an actual operation it has to do. It basically goes, gets the data, and then returns it. This round trip is, in modern terms, comparatively slow. It takes time and cycles to reach out to memory and grab the data. So what all modern CPUs have is a concept of a cache. So inside the silicon itself, it has, you can think of it as like a mini RAM. When it fetches data, it will then load it into here so that the next time your program needs it, it can get it from the CPU, it can get it from the cache rather than reaching out to memory. So this is kind of like a pretty standard optimization that your hardware provides for you. So that's kind of just going over the cache architecture. It talks specifically about the Apple M1 silicon architecture, which is kind of interesting. So within your CPU, you will have multiple cores, which can all run code concurrently. And depending on the architecture, you'll have different levels of cache. So what this is saying is that the Apple M1's cache has a core private L1 and then a shared L2. So what that basically means is every core has its own L1 private cache, which can be different per core. And then shared amongst all of them is a common L2 cache. So that's kind of just setting the scene of the cache hierarchy in the chips that they are going to be exploiting. So then it goes on to what a cache side channel attack is. But before we get into that, we really kind of have to have a rough idea of what a side channel attack is. So a side channel attack is where you attack the implementation rather than the underlying algorithm. So let's assume you have some crypto primitive, and all the crypto experts and mathematicians have gotten together and said, yep, this is secure. They've anointed it with whatever holy water they need to, and everyone's decided that, yes, this is good. That's all good on paper, but at some point you actually have to write that in code. So what a side channel attack does is exploit weaknesses in the implementation rather than the underlying maths. The classic example of this is a timing attack on password checking. So let's say I have some code which is going to check an input against a known password. So say I have a password. Right. So this is the secret, and then at some point someone inputs a guess, which is their attempt at the password. If you were to think how you might do this in code, you might do something like for int I equals 0, I is less than the the strlen of the password. It's a little bit bigger. Plus I. And if guess of I doesn't equal secret I, Photoshop is not a good code editor. Break. So you might imagine that this might roughly be the code that you would write to check a password. You go through every single character, and then you check that for each character in your guess, is it the same as the one in the password? And then if it's not, you break out and you handle that case. The problem with this is that it does leak some information about the secret. So if you imagine as an attacker, I can have as many guesses as I want, and I'm going to guess for the first character A, and then I guess B, and then C, blah, blah, blah. In each iteration of this loop, we will go, hey, does A equal P? No, break. Does B equal P? No, break. But at some point, if we go through every combination, we'll eventually hit P, and we're like, yes, this does match. So we'll then go through to the next iteration of the loop, where I can then, have another guess. So in theory, if you can time this code, like time the execution of it to a reasonably high precision, you will know when you've guessed the first character correct, because it will then do one additional iteration of the loop. It will take ever so slightly longer to execute. And this is a side channel attack. You're not breaking the logic for checking the password. You're not doing any sort of buffer overflow. You're not doing any sort of actual exploitation. All you're doing is observing the side effects of the code and exploiting that. So if we go back to the article, this basically says a cache side channel attack is an attack that infers a victim's program secret by observing the side effect of the victim's program's secret dependent accesses on the processor cache. So what that's basically saying is, if you can observe something about how the cache, the latency or the misses or the hits, if your secret somehow interacts with the cache and you can observe it, then that will potentially leak some information about your secret. Again, you're not attacking any particular implementation. You're just saying, hey, I've noticed that the code does certain things when the secret is in this state. And it kind of breaks it down a little bit more information here. It says, these attacks typically consist of 3 steps, during which the attacker 1. Brings the cache into a known state, 2. Lets the victim execute, and 3. Checks the state of the cache to learn information about the victim's execution during step 2. So the next thing the paper says we need to know about is classical prefetchers. And this is a hardware optimization to hide memory access latency. So as before, we were talking about there's some code which does some access, and then the CPU reaches out into memory. So it reaches out to memory and brings it back and then sticks it in a cache so that if you need that particular value later, it's much quicker for it to retrieve it. However, what a prefetcher does is say basically, look, if you're accessing this data here, there's a high chance you're going to want this data here and this data here. So instead of it just bringing back X into the cache, what it'll also do is it'll also at the same time bring back Y and Z. So it will pre-fetch data it thinks you're going to need. And this makes sense, right? Because often you'll be looping through an array. And if you're looping through an array, you're going to want to access every single element. So when you access the first one, when it'll find that it's not in the cache, it'll reach out to memory, it'll bring it back, but also bring like the next values with it. So that when we come to iterate on the next element, it's already in the cache, and therefore it's a lot faster. So this is what it's referring to as a classic prefetcher. All hardware basically does this. It makes a lot of sense. This is why arrays are so fast, because they're very friendly to your cache. All your data is stored congruently, so next to each other in memory, so that when you access the first element, the next few elements will almost certainly be in your cache ready to go. And this is why in C++ land, a lot of people advocate for stood vector, because it is a dynamic array, which ensures everything is stored congruently in memory. So if you have a stood vector and you iterate through it, it's very friendly to your cache because it will bring back additional elements for you as you start iterating through it. So what Apple have done is added into their silicon this thing called a data memory dependent prefetcher. So what this basically says is when I'm accessing data, in an array, in addition to doing the classic prefetch of taking this element and then the next ones, it actually introspects the data in here and says, hey, if X is actually a pointer to some data way away, then there's a high chance that if I'm accessing this data, I will also want to access the data this points to. So it'll also pull back this into the cache. This is useful for traversing things like linked lists, where each node will definitely not be next to each other in memory, but it'll have a pointer to the data it needs. So this can kind of speed up those. I guess another scenario this might be useful for is if, say, you have a std vector of unique pointers. Each pointer will be next to each other in memory, but the actual data you probably want will be sporadically spread over your heap. So using a DMP, when you're iterating through that list of unique pointers, it can then also cache the data you're probably going to want to access as you're doing that iteration. So what this paper is basically saying is that through the use of DMP, that caching of pointer data could potentially leak information about the data that it is operating on. So if we go down here to some actual code, we actually care only really about this snippet on the right, because this snippet on the left is based on some previous research. It's saying that if you have an array of pointers called AOP, and if you fill that AOP with pointers to unique addresses, and then run this code here, the mere act of just reading that pointer, all right, of just iterating through this array of pointers, will bring the data that is pointing to into the cache. So they basically run an experiment where they generate a load of new unique addresses, probably through calls to malloc or something like that. So they've got a whole bunch of these. Unique addresses, a prime, whatever, and then they create this AOP array, and in one instance they make that equal to these unique addresses. And then in a second iteration, they do AOP equals some random values. So I don't know, OXAABB, OXCC, whatever. Something that's not a pointer, right? So they generate these unique addresses, and then they, in one instance, create an array of pointers to these addresses, and then in another instance they create an array to random data. They then run this loop, which then literally just accesses each member of that array, doesn't do anything, doesn't try and dereference the data, just literally reads from every element in that array. So then read AOP, right? And then after that they time the latency to all these addresses. So it all boils down to these graphs here. So what they've observed is that if you access these unique addresses when a pointer to them has already been read, then it is much, much quicker to read from those addresses. So you can kind of think of this as just like summarizing what the DMP does, and in an observable way. If we have data that looks like a pointer, then the DMP will cache the data that is being pointed to, so that when we access it later, it's much faster. So the next part of the paper is the DMP activation criteria. So what they've done is run a whole bunch of experiments to reverse engineer how the DMP actually works and what criteria it has for reaching into memory and caching it. So basically how it works is that when an L1 line is filled, so it's filled up a cached line, the DMP will then kick in and scan that memory. It will scan that in pointer size aligned chunks. So it will go through each 64-bit chunk of data and perform an address check on that. So that checks certain bits and basically has a heuristic attempt at deciding if that is a pointer, and also if that's a pointer it's not seen before, and if all those criteria are met, it's like, okay, this I think this is data the user is going to want, so I'll reach out and I'll cache it. It's got this concept of do not scan and a history, so it's not always going to do it. It's going to be based on whether it's new data, but effectively they've kind of got a reasonable understanding at this point of how the DMP behaves. So this next part of the paper I think is really interesting because it applies these findings to a very specific small case, which kind of really helps you understand what it's doing, and then it uses that as a building block for more advanced exploitation techniques. So what they're going to do is use these features of the DMP to break a constant time function. So when you're implementing crypto algorithms, you really want them to be constant time. That means that regardless of the input, the algorithm always takes the same amount of time to run. So if you think back to our example where we had the password checking, that was not a constant time function. The runtime of the function was actually dependent on the secret. So to make that a constant time function, what you would do is just always loop through every single character and check it, regardless of whether you knew it was already incorrect. So a lot of crypto libraries will try and implement as much as they can at constant time, because that means that it's not leaking information. The secret has no, regardless of what the secret is, it doesn't affect the runtime of the function, which means it doesn't leak information about it. So they've got an example here called CT swap, so constant time swap, which actually is based on code from OpenSSL. So what this does is it takes two arrays of the same length and conditionally swaps them based on a secret. So if this secret is 0, then they don't get swapped. But if the secret is 1, then they do get swapped, i.e. every element in A becomes every element in B, and every element in B becomes the equivalent element in A. So if you or I were to program this, we would probably do, if secret is 1, do the swap, else don't do anything. However, this causes the function to leak information. Doing the swap will take more time than not doing the swap. So if you were to be able to observe and time this, you would see that, every time the secret is 1, it takes a little bit longer. It's kind of worth just going through this code anyway, because I think it's really interesting. But what this code does is it does the swap in constant time. So regardless of whether the secret is 0 or 1, i.e. regardless of whether the end effect is that the data is swapped or not, it still takes the same amount of time. So it does this in quite a clever way. The first thing it does is extend the secret to be a machine-sized word length. So if secret is the value 0, then it should remain 0, 0, 0, 0. However, if the secret is 1, it needs to be turned into the form FFFFFFFF. Now, again, you could just do if secret is 1, secret equals FFFFFF, but your logic flow then depends on the value of a secret, which you can't do. So how do you do that in constant time? And it does this with this clever little bit twiddling hack. So it takes the secret, subtracts 1, and then negates it. So our secret can only be 0 or 1. So if it's 0, 0 minus 1 is minus 1, which is FFFFFFFFF. And then if you negate that, you'll become 0, 0, 0, 0, 0. So by doing this with an input of 0, you will end up still with 0. However, if you give it an input of 1, 1 minus 1 is 0, which is 0, 0, 0, 0, 0. And then if you negate that, you'll end up with F, 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 F. So this will give you the desired result in constant time, regardless of the input. The next thing it does is loop through every single element in the array. Again, it has to do that regardless of whether it's going to do the swap or not, so it can be in constant time. And the first thing it does is take both elements in each array and XOR them together, so that kind of mixes them together, and it then ANDs them with the mask. So if the mask is 0, then it will zero out this value, because any number ANDed with 0 is 0. So when the secret is 0, the delta will always be 0. However, when the secret is 1, it will AND it with a mask of FFFFF, which leaves the value unchanged. So you can now see on each iteration through this loop, delta will either be 0 when the secret is 0, or A1 XORed with B1 when the secret is 1. And then what it does is it then XORs itself with the delta. So we take AI and make that equal to AI XORed with the delta. So what this means is that when the delta is 0, this will remain unchanged, because any number XORed with 0 doesn't affect it. So when the secret is 0, AI will just equal to AI, so it remains unchanged. However, if it is 1, then delta equals AI XORed BI. So what you'll find is then that sets AI to be equal to AI XORed with AI XORed with BI, right? Because that comes from the delta. And then these cancel out so that you end up with AI is equal to BI, and the same applies for the B side. So this is how it can conditionally swap two arrays in constant time. So what the paper then goes on to do is then attack this implementation by exploiting the features of the DMP. So we now overview how the attacker uses the DMP to extract the secret. At a high level, the attacker populates one of CT-swap's arrays, either A or B, let's assume B, with a pointer of its choosing, and then arranges for the DMP to dereference the contents of the other array, A, during the conditional swap computation. And then, I love this bit, then the attacker uses conventional cache side channel analysis, just the regular side channel analysis that everyone knows how to do, to observe whether the pointer was dereferenced by the DMP due to the swap computation over A. So effectively, the attacker can control either of these arrays. It's going to fill B with a pointer in such a way that the DMP will be triggered only if the secret is 1, and then it will then measure the latency to kind of ascertain whether the DMP was triggered or not. That's effectively what this is going to do. The actual nitty-gritty details of this are quite involved, because it even says that, however, it is not clear how to build eviction sets for pointers target line. They basically admit that just given that high level approach, they cannot influence the cache in such a way to make this viable. So then you get onto the next section, which is but we've got this novel technique for doing it. And this is in depth, and I will admit I've not had a chance to fully work through this yet, but basically they generate a standard set of eviction sets, i.e. a standard set of data which they know can evict data from the L2 cache. They then narrow that down to which of these are capable of evicting just the pointer from the cache, and then basically using that information they can kind of run a series of experiments to understand whether the DMP was triggered or not. So they perform 3,200 attacks for both values of secret. So using this novel technique they've developed, and then timing latency around the DMP, they can see that the latency when the secret is 0 is in this section, and then the latency when the secret is 1 is in this section. So hopefully you can see by just looking at the graph that it's pretty clear using this technique when the secret is 0 and 1. So this effectively allows you to leak the secret. So this technique allows you to leak one bit of data, but it doesn't really end there, because they then take that as a primitive and extrapolate it to real-world crypto libraries. So I'm going to skip over the Go one just because I'm not really that familiar with Go, but what I am interested in is the OpenSSL Diffie-Hellman key exchange. So for anyone not aware, the Diffie-Hellman key exchange is a way for two parties to arrive at a shared secret through a unsecure communication channel. So the idea is that those two parties can exchange information in such a way that they both arrive with the same answer, but anyone observing that communication can't also then infer that answer. And really the best way of explaining it is just the paint example on Wikipedia. I think this is absolutely brilliant. So you've got two parties, Alice and Bob, and you can imagine that they're communicating over an insecure channel, so that anyone sitting between them, monitoring what they're saying to each other, can access all that information. So either Alice or Bob generate a common paint color, which they share with between each other, so both Alice and Bob and any attackers know the common paint color. They then each separately generate a secret color, which they don't share with anyone. So Alice creates orange and Bob creates teal. They then privately mix those with the common color. So Alice ends up with this orangey salmon color, and Bob ends up with this light blue azure color. They then transfer this mixed paint to each other. So again, an attacker can see this color, and they know the yellow color. But, and the key point here is that it is very expensive to separate out these colors. So if an attacker was given yellow and blue, they could not feasibly infer green. So then on both sides, once they each have their sort of shared mixed paint, they then mix in their own secret, which again hasn't been transferred over, and they both arrive at this delightfully shared brown secret color. So that's effectively the Diffie-Hellman key exchange, and that is used all the time to share secrets. Whenever you see the padlock icon, and that means you're using TLS, there's a high chance that you have used Diffie-Hellman with the server to arrive at a common secret, and that common secret will probably be like an AES key for like bulk encryption. So anyway, that's the high level view of Diffie-Hellman. It's really interesting, if you want to dive deep into that. So they take the Diffie-Hellman implementation in OpenSSL, and what they're looking for basically is something that looks a bit like this. They're looking for a constant time function which, given a certain crafted input, will trigger the DMP in such a way that they can then observe it and then infer information about the secret. So again, this kind of just goes through an overview of what Diffie-Hellman is. Alice and Bob agree on a shared secret that requires P to be a safe prime. Don't want to use an unsafe prime. That's a big no-no. It goes through a little bit of the maths. And then they basically say that it boils down to this code here, and they claim that the bn mul mont fixed top function, which is a constant time function with a specifically crafted input, can trigger DMP in such a way that an attacker can then observe that and then infer information about the key. And then it goes through a whole bunch of maths, which I have not really looked at since university, and I would need a primer on it to really fully grok what all this does. But the really interesting part is the experimental results. So they basically said that they did all the work, and that it took 2.3 hours to complete, and that after that they managed to extract the victim's key. So the whole point of this is that it's a local exploit. So someone would have had to have been sat at your machine for 2.3 hours in order to break the key. So that kind of tells you a bit about the feasibility of this attack. And in fact, if we go right to the top of the paper, there's something I forgot to mention right at the beginning, which is that they disclosed this exploit to Apple, OpenSSL, GoCrypt2, and the Crystals team. And OpenSSL reported that this local side channel attack falls outside of their threat model. So if OpenSSL don't care about this, how much do you care about this? And then after the OpenSSL attack, they then look at attacking some post-quantum cryptography libraries. So I know very little about post-quantum cryptography libraries. I assume they are ones that don't rely on prime factorization and are therefore not susceptible to Shor's algorithm. The last time I looked at any of these was back in university, which was quite some time ago, and I think lattice-based crypto algorithms were the new hotness at the time, but I don't know if that's still the case. But yeah, so if you take a step back, this is a local exploit. It requires someone to be at your computer for a significant amount of time in order to break any sort of these crypto algorithms. But the key takeaway for me is what this paper represents. This represents, the next step in these kind of cache-based attacks. So whilst the outcome of this might not be applicable to you, the next set of researchers who come along and do the next thing, or the next set of researchers after them who come along and push it a little bit further, you can kind of see how eventually this might end up in a remotely in an exploit that you can trigger remotely, which is a concern. So this is a great paper. I really enjoyed it. There's lots of really good details in here. I'm really hoping at some point they might release a proof of concept code sample, because I'd love to actually sit down with this and have a play around with it and run through it myself to really see how it works. But yeah, I'll leave a link to this in the description. But if you want to see some actual practical low-level shenanigans, then check out this next video.